Okay, welcome back. This is my third hour speaking in this hall. I continue speaking, I'm dying. Okay, welcome back. So let's talk about what we have learned so far. So in the first two lectures, we talked about the supervised learning. So we have the mapping from X to Y. And last week, we started to talk about unsupervised learning in the context of clustering and density estimation with GMM. And today, we will talk about another task of unsupervised learning, why this is not working. Ooh. Okay, so the plan for today is to talk a little bit of the other task of unsupervised learning, which is reducing the dimension. So one of the canonical tool for a dimension reduction is what we call the PCA. Most of you might know this already, but it turns out that the math is actually more hairy than I thought. So the algorithmically is quite straightforward. But again, just to walk you through some of the math a lot behind. So the idea of dimension reduction, especially in PCA, is to say we started with some high dimensional space, but we try to do some projection onto some lower dimensional manifold. And because of that, we need to talk about how do we project in terms of the vectors. And then we talk about what we try to achieve here. So just like any machine learning, we need to talk about what is the loss function. And in PCA, we are making the assumption that the direction with the maximum variance contain the most information. And we talk about how we formulate that. And from that, we will see that algorithmically, as long as you can calculate the covariances of the data and is able to diagonalize the matrices, then you will get the direction that you want. Unfortunately, this do require some understanding on the linear algebra, especially the diagonalization and eigenvector and eigen values. If this is somewhat a foreign ideas, let me know. I will send you some resources to understand that. I also believe like 3 Blue 1 Brown has a pretty good video on the diagonalization. So let's talk about the motivation. Like, why do we want to do the dimension reduction? A large part of that is because many data inside or outside astronomy is quite high dimensional. So the images, spectra, they all have like thousands of pixels. Like even you're thinking about the elemental like abundances of star, you will have like few tens of them. And of course, it's very hard to understand or visualize the collective behavior state of a spectrum. Right, when you can plot one example, but it's very hard to see the trend and the properties. And this is why being able to compress the information helps you to understand the underlying like data. First, of course, they are quite expensive to store. So if you compress that, then you save some of the storage. And one of the good news, especially in astronomy, is that most of the dimension that we have is over complete. So what this means is that most of the pixels are highly correlated, or your properties are highly correlated. And that is just born out from the fact that astrophysics is very simple. I think that's sort of the misconception about people. You tell your public you study like astrophysics. People are like, wow, you study astrophysics. But it's actually like the simplest thing like you can do in science, because the guiding principle is always very low dimensional, right? Think about, you can predict the orbits of a binary based on the pure equation. Certainly you cannot like predict my motion, right? Because I am a more complex being than a star. And the astrophysics, most of the phenomena that we see come from some finite of physics that generate the observation. And therefore they are by definition quite low dimensional. So there are hopes that we can project the data into this more physical, low dimensional space. So talking about like a dimension reduction, this is a 101 example. So let's say I have two features, x1 and x2. you can see that in this case, most of the variants are in X1, and X2 is kind of a small, there's only small like changes. So you can imagine, of course, if I just keep the value of X1 and just disregard the value of X2, I would not have lost some like most of the information. And this is, of course, making the assumption that the information come from the variability of the objects, which is quite reasonable. So let's say if you want to understand the properties of a population, say in a human being, you want to find the features where human to human, there's a big variability. So those features that are just like constant for all population, it will not be that informative. That say, in many like cases, in this case, if you just throw away the data, you halve the storage, right? So now instead of like keeping 2-dimensional, you keep like 1-dimensional. But in real life, it's not that simple because in many cases, all of the information are informative, or just that they are highly correlated. So a good example will be the example that we use in the beginning of, let me try to move away. Keynotes and Zoom do not really work too well together, I realize. Okay. So let's say we take the example of the real estate in Canberra, again, which is horrendous. If you plot the prices and the area, you expect that a bigger houses is more pricey. So let's say they are really strongly correlated and form a line. Then you also imagine that, in fact, both of them are informative, but if I know one, I can predict the other. So meaning that instead of storing 2 dimensions, I can just store 1 dimension. But with a catch, right? So ideally, you want to store information, not only one of the information and predict the other, you also want to be able to understand the degeneracy, the direction of the degeneracy. Meaning that instead of like dealing with the original like axis, the best way might be just turn the axis into the correct frame and then just store, like if you call this X1 and like the other one X2, then you can just store the value of X1 in the new axis and just discarding the X2. So you achieve 2 things at once. One is that you compress the information, but also from the direction of your principal like component, which we will talk about how we find that. You are also like determining the direction of the degeneracy. Like PCA is very, very simple, but also have like a lot of application. So I will talk about this paper that I did as a student here, like before I do my PhD. Good paper, level with Ken when Ken is still younger. I'm not too young, like 10 years ago. This is like literally 5 lines of code. All right, so and on 200 star because like there's no Gala then. This paper is cited like 138 8 times. Still like one of my most cited paper. Of course, if you have only a 300 star and 20 the dimension, the goal here is not to compress the information, but what is really interesting here is to say most of the chemical properties of star are highly correlated. And they are highly correlated because all of the properties of the star come from the previous generation of supernova. So if you like assume there is only like 3 types of supernova, then you would expect the data form a low dimensional like manifold. So let's say if you have only 1 type of supernova, they give you always the same relative like ratio. Then as more supernova happens, you only form in a 1 direction. I actually love this plot. I made this as an undergraduate. Amazing. Right. So but it's more important than that, right? So but of course, we have more than 1 supernova. So we have like a manifold in the 30 dimensional space. And by understanding the direction of the principal like component, you kind of understand how many type of supernova we have. And in this paper, I think like one of the main result is we actually find that the support what we call the hypernova. There's something more like the energetic or supernova that will give you another tangential direction. So So that's old work, but PCA still goes strong. So this is another example that I show in the beginning of the courses. So this is a slightly more advanced PCA. We call the latent factor analysis, which is done this year. So you are doing that a little bit on your assignment tree, but where you're looking at the quasar like continuum. The quasar like continuum is extracted with some of this technique. In practice, it's more tricky because not only you have the observation, not only you have the continuum, you also have the absorption from the intergalactic medium. So technically, this paper combined three things that you will learn in the next few lectures: PCA, Gaussian process, and a neural network. When you combine all of them, like, you can do a pretty good job at reconstructing the continuum. So meaning that like despite like today might be one of the simplest lecture, you have only like 5 lines of code, but most of them is still very, very like powerful, like if you know what you are looking for. So let's set up the mathematics settings for PCA. So just like last time, we only have the feature X. We do not have the labels Y. And we assume the data set to be IID, stand for independent and identical distributed. Meaning that, I have some underlying like distribution, like what we have learned last time, a generative models try to estimate the distribution. My data is drawn from this distribution. They are identical in the sense that they are from the same distribution, even though they are not exactly the same. You can think about if I want to collect the outcome of the dice, that will be IID because individual row is independent. The outcome itself might not be the same, but they are all drawn from the same uniform distribution. So the goal here is that I have a bunch of X, and first of all, as we will see, is always very practical for PCA. Not practical, actually, you have to shift the data to mean a 0 for some of the proof that we will see today. So we will assume the data to have mean 0. If this is not the case, which is most of the cases in astronomy, take spectral for example, the flux is always straightly positive. So you are definitely not mean 0, but you can always shift for individual variable, for individual pixel in the spectrum to have a mean 0. And the goal here is to find a projection Z that is, of course, much lower dimensional than X, that will be similar in some sense to the original data X. So do you have any question? Oh, my class is always so clear. So the key insights here, we have like we mentioned, like if you take this example, it seems like the correct direction that I want to discard here is X2, because X1 have more variance. So I want to keep the direction that have the most variance. So of course, this might not be exactly true in many cases in astronomy. Imagine, some of the variances, we kind of know the physical mechanism, but it's rather the small variances that we want to capture. Those can happen, but it just means that you need to re-weight your features in that case. The goal here is to, in the more a generic sense, you want to find the rotation such that you capture both the degeneracy as well as the dimension, right? And the goal here, of course, the problem is that we do not know what is the projection a priori. It's very easy in two-dimensional case and say, well, here, right? But if you have thousands of a dimension, then finding the correct vector in these thousands of a dimension is very difficult. So this is the setting. So you want to find the direction that you want to project your data such that you keep the most variance after the projection. So the goal here is to find such a B in a algorithmically way that is independent of the dimension. Right. So of course, to do this, we also need to just do some revision on the vector of projection. If you came to my colloquium just now, you know that you can do dot product, right? That's very helpful. So if I have a vector X and I want to like project that to a vector B, the way that I would do that is to do B dot X, or like written as B transpose X. If I want to like recover the vector, of course, I also need to append the direction of the vectors. So it's B dot X times B, right? So B dot X is a scalar, which is the coefficient, and B is the direction. And something that will become very useful in this lecture is the covariance of the data. So the data, like covariances, is just how much spread that you have in the data. And by a definition of the covariances, is just x minus mu dot x minus mu like divided by the length. But because we assume that the data is mean 0, so this is simplified. So you only have x dot x, right? So this is the data covariance, which is actually a RD times RD like matrices. So each time you dot here, you actually get a matrices because you are doing like column dot row, right? Okay, so the goal here, like mathematically speaking, is I want to find a set of B's from 1 to D equals to 1 to big D, such that it spans the whole space. Of course, if I take all D dimension, then I'm just like rotating my axis. So I'm doing like nothing, right? So if I started with a D-dimensional space, if I keep D non-degenerate vector and decomposing them, of course, they will still be full rank, and therefore you are just like redefining the axis. The goal here, of course, is to split that into two parts. First part from 1 to M, and the other second part from M plus 1 to D. And you want to say the first part is what I want to keep, like projecting to the manifold, and the second part is what I want to discard. The goal is how do I find this set of D, right? A B of D. One notation, right? So the BM dot X here is just the coefficient of that new direction. So any question? Good. So maximum variance of formalism. So let's talk about how we want to formulate the loss. The goal, like remember, we want to find the direction, or this D set of new vectors. But let's talk about like finding the first one. So let's say I want to find only in this D dimension, I want to project all the data into one direction that I call B1, such that it will keep the most variance. Luckily, when you do a linear like combination, you do not shift the mean. So after you have rotate the axis, you still have mean 0. If you have a mean 0 in one direction, then the spread like along this direction is just the quadrature sum of the coefficient. In practice, I usually have like minus the mean, but again, the mean is 0. So meaning that if I project all my data X onto some unknown B1, the coefficient will be Z1. And the variance of all the data like along B1 will be the Z1n square, summing all of them, looking at the variance of the distribution in 1D. Is this clear? Cool. So let's talk about, like, based on this loss, how do we find B1? So we can just rewrite Z1n is just the dot product of B1n and Xn. I can rewrite this into, like, if I have two, like even though this is a scalar, if I write that in the vector form, I can do the vector dot the transpose of the vectors, right? So I get B1 transpose Xn, Xn transpose B1. B1 itself, of course, is independent of n, so it can be pulled out from the summation. So you get to this point, and this looks very, very familiar, which is the covariance matrix of the data. So you get to the variance of this newly projected data is just this unknown B1 that I want to optimize times S times B1. So the question is that what B1 can optimize this? So we want to find B1 that maximizes this term, which is a scalar, with some constraint, because I want the vector itself to be a unit vector, because it is sort of the axis of your new direction. So you have a terms that you want to optimize with a constraint, right? So we have learned this last time. If you have fx that you want to optimize with respect to x with a constraint gx equals to 0, then you use Lagrange multiplier. So meaning that instead of optimizing B1 this term, also have this constraint. This can be written as 1 minus this to be 0. This is just the Euclidean norm, which is B1 transpose times B. So to do that in the Lagrange multiplier, you will extend this with a auxiliary variable lambda 1. And then you want to optimize this term with respect to B1 and lambda 1. And the way that you would do that, just like mechanics as usual, you just differentiate that with respect to B1 and lambda 1 to see what you get. So if you differentiate that with respect to B1, you get this term. If you differentiate that with lambda 1, you just get this term. This term, of course, is quite redundant, because if I set this to 0, it just means that I have the norm of B1 to be 1, which is the constraint that we impose. This one term itself is actually interesting. If I set this to be 0, I have B1 transpose S equals to lambda 1 B1 transpose. I can take the transpose of the whole thing. I will get S transpose B1 equals to lambda B1. But S, of course, is a symmetric matrix, because it's the covariance matrix. So S transpose is just S. So you get to this term. So recap, I do not know what is B1, but I want to optimize the variance of the spread. And then naturally, I find that in order to satisfy that, I need to satisfy this set of equation. And this really looks very familiar for people who have taken linear algebra. You say a matrix dot the vector equals to the vector itself, meaning that this is an invariance direction that we call the eigenvectors, right? So meaning that the one B1 that would maximizes the Lagrangian here will be the eigenvectors. It has to satisfy that. The question is like which one, right? So I have like a loss of eigenvectors. So which one will maximize that? That is actually quite straightforward as well, because now I know that this B1 has to be a eigenvector. So I can turn SB1 to be lambda 1 B1. And of course, B transpose B1 is just a unit vectors. So this can cancel off equals to lambda 1. So I have a set of the B1 that I can choose from, exactly D of them, if the matrix is full rank. The one that will maximize the term V1, of course, is the one with the largest lambda 1. So taking all this together, it means that if I want to project some d-dimensional data into one dimensional space, the direction that I should take is the eigenvector of the data covariance matrix S, and I should choose the one with the largest eigenvalue, so that will maximizes the variance after the projection. Question? Yep.
Variance depends a lot on what units
you're
working.
Yeah.
So if we've got a multi-dimensional space, like not easily
comparable
units, how do you tell what actually has the variance?
Yeah, so we come back to that point later. So this is again like a choice. The simplest one is just to normalize over the unit. You just say I will take the data each dimension. I will normalize that with respect to the variance of that dimension. There is a choice and assumption to make that depend on the domain knowledge. But it's such a very good point. In many things, your features have the same unit. So how do you define that? Right? Does that answer your question? Okay. Question? Cool. Okay. This is the simplest part because we find the first B1. Now we want to find M of them, right? So that's a tricky part. Of course, like D can be very large, and therefore the M dimension that you should keep can be also like very large. So you certainly like do not want to do one by one. So search B1, B2, B3. So you have a long sequence of things that you want to prove. The easiest to think about this is, well, if this is true, so it seems like if I want to keep M dimension, it seems natural that I would just keep all the eigenvectors that have the M largest eigenvalues and keep it and call it a day. In fact, most lecture we just stop here to say, oh, this is true, done, let's move on. Not here, right? So do math, yeah. So we'll prove that this is indeed true, right? Your intuition that I should keep the M eigenvectors that corresponding to the M largest eigenvalues in the data matrix S. There are lots of like repeat term. I will say this a lot of time. It's very tight. Yeah. I just hope that I just like ChatGPT myself, just like split out the words. So we have not only show that like this is true for the first dimension. I want to show that this is true for M dimension. You have a sequence of statements they want to show, meaning that the second dimension that I should keep is the second largest, the eigenvector with the second largest eigenvalue. The third dimension is the same, right? So I want to prove all these statements. Of course, you do not want to prove that one by one. Hopefully, you have learned this from your 1000 level math courses. I think it's like called proof of induction. Just a very useful trick. So proof by induction is just saying that if I want to prove a sequence of statements, I will first show that it's true for the base case, either n equals to 1 or n equals to 0, which is what we have done. Then you have the inductive steps, meaning that assuming that m minus 1 is correct, then m is also true. So this is, of course, quite logical. It just means that if the 0 case is correct, then the 1 case is correct. And because if the 1 case is correct, the second case is correct. So you can just, by proving these two things, you can show that this statement is true for all m's, right? So that's what we want to show. And we want to show that this is true for the statement that we just made. So just recap what is the statement that we just made. We say that, so we have proved the base case. So we want to prove the induction case. So the induction case say, if the first m minus 1 eigenvector that I should keep is the one that is the eigenvector of S with the m minus 1 largest eigenvalue, then the next one that I should keep is the mth eigenvectors. And I want to make sure that this direction indeed will maximizes the remaining of the data variance. That's the statement. This is very like mouthful, but when we write down some math, hopefully this will become clear. So to make things more compact, because now we have a bunch of data X, we can put that into a column like vectors. So it will be RD times N space. If I want to project all the data into one direction, I can just do the same dot product, but instead of using one column at a time, I will just dot the whole square, not square, a rectangular matrices with B1, right? So if I have already taken m minus 1 of them, then the projection will just be the sum of all this, right? And what is the new data? So after I have projected the m like minus 1, the remaining like data will be X, the original data minus the projection, right? So that's the remaining variance that you could extract. And this can also be written as just a simple form in matrices, X minus BB transpose X, which we call X hat. What we try to do here is to find the direction that will maximize the extraction of the variance from X hat. So like I have a new transform like data. I will call the new data covariances to be S hat. In order for the induction step to be true, what we want is to say that the direction that I should keep is indeed the same eigenvector of the original S, but it's the nth of them, right? I want to make sure that if this is true, then the induction is completed. Take a step back, like there are lots of statements, right? So we say that the n-1 is correct. So I have projected my data into this n-1 dimensional subspaces. I have the remaining information that I call x hat. I calculate x hat, and then I have the data covariances s hat, right? And I want to say, among this direction, I should always take the direction that is the same as what I would have taken in the original data covariances S with the mth eigen value. I'm not sure that's helping. I'm just regurgitating, but hopefully this is clear. Is that clear? Question? No problem. Okay. So let's look at this covariance matrix. So hopefully these properties again, right? So there are some bit and pieces of math. The hard part about machine learning is that there are lots of bit and pieces of math. Some of that you have learned in different courses. To put them together is always hard. But if this is not super clear, really is a ChatGPT prompt away from understanding. So you do not need to take a full courses to understand all these things. Some of this is interesting facts, right? So if I want to take the covariances of x hat, this is an operation of x hat. I already know x hat can be written as x minus bb transpose x. One nice thing about the covariance operation is that it's bilinear, meaning that I can expand this out to the different quadratic term, cross term, and the quadratic terms. This seems a bit fuzzy, but if you just write down the definition of covariances in the context of sum over one, n equals to 1 to n, and do the dot product, then you will see this to be true. So let's simplify these things a little bit. First term we already know. This is just S. Let's talk about the last term, right? Let's start with the hard one first. So the last term here, we use another fact that because the covariances is bilinear, so I can pull out any constant matrices from both sides. So the covariances of AX and BY is just A covariances XY times B transpose. So if I write this down, I can pull out BB transpose and BB transpose. Because BB transpose itself is a symmetric matrix in general, right? So if I do a transpose operation, I will just swap the order and take the transpose, which become BB transpose. So this means that this term is equivalent to this thing. This is getting very handy because I know what this is, right? So this is just S. And also know that what B is, because B consists of all the m-1 column vectors that I have extracted by the assumption of the induction. They are the eigen vectors of S, which means that this thing, the S and times B, is a diagonal matrix, because now I have a bunch of eigenvectors, not just one. So this is equivalent to SB times the lambda B, where lambda is the diagonal matrix. And once you have the diagonal matrix, this becomes very handy because this becomes lambda times B, where lambda can be pulled out to the front. It's a diagonal matrix. So you encounter B transpose B. But B transpose B is identity. Why? First, there are eigenvectors. B, they are the eigenvectors of a symmetric matrix, which is a covariance matrix. I think you also need positive or definite, but S is definitely positive definite. For all the symmetric matrices, the eigenvector is orthogonal. In fact, I also assume that B are all unit vectors because by the proof of induction, so exactly I have the identity matrix. So I cancel off the middle terms and just get to some lambda BB transpose. So B transpose B is identity, but BB transpose is not. So I will keep this lambda times BB transpose. just walk through the math. So we have done the last term. The second term is easier. I have -2, the covariances XBB or transpose X. This is just a linear term that I can pull out, take the transpose of the whole thing. It turns out to be the same thing. So it'd be the 2 times the covariances B times B or transpose. Right. So this is just S. I again encounter S and B that give me -2 lambda BB transpose. Very hairy, but it just comes down to, if I'm combining all the calculation, I will get the covariances of S hat is just S minus lambda BB transpose. Nice thing will happen now, after all this math, right? This is the part that I'm not sure you like this. It's easy to check. In fact, it's very easy to check that this thing have the same eigen vector as S. Why? If I dot this with some B matrices, they're all orthogonal. So either you get an identity or 0. So you will pass through this. And then when I do S dot that B, it will also be just some lambda B. So you will get back to S hat dot any B, which is the eigenvector of S, we always get back to a constant times B. So this thing have the same eigen vector as S, but with one key differences. So if I take the first m-1 eigenvectors, when I do S dot B, I will get the lambda times B, but the lambda now get absorbed by this term because I have the minus this term. So even though I have exactly the same eigenvector, but the first m-1 of them no longer is the largest, no longer are the direction with the largest eigenvalue, because they get all absorbed by these terms. In fact, those have the eigenvalue of 0. So what is the largest one next? Which is m, right? So you have exhausted all the m-1. So the direction that will optimizes the variances of S hat is the mth eigenvectors of the original eigenvector of S, because the other m-1, you have a eigenvalue of 0. Voila, proof. Done, right? QED. So we have done the induction steps, and this is why, just now I talked to Irving, and it's PCA, do you need a lecture? Kind of, you need this to show that this is true. By the way, I wrote down the proof myself, so hopefully I didn't make any mistake, but I think it's logically clear. The first version that I uploaded is actually there are some mistake. Any question on this proof of induction? If all this seems too mathematical, just forget about that. It's fine. So what you need to do is, I take the data, I calculate the covariance matrix. That's one line of NumPy. Second line of NumPy, do the diagonalization. Keep the first m of them. Done, right? That's the main point. If I want to project the data to keep the most variances, is as simple as just taking the covariances of the data, do the diagonalization, and keep the mth eigenvectors that contain the largest eigen values. But there's still one thing to solve, which is how big the m is, right? So if I take m equals to d, then I'm doing nothing. Of course, I want to take m is smaller than d. Luckily, in order to determine how many components that you want to keep, you have already done all the calculation that is needed. Why? Because we have shown that whenever I project to any mth principal or component, if I take the eigenvectors, the variance captured by this particular projection is lambda m. And because all the eigenvectors are orthogonal, because S is symmetric, therefore you can just sum up all the variances from all the direction. So if I want to ask how many variants I have captured up to the mth dimension, then it will be just a summing all the variances from 1 to the m the direction that I will define. That will give me the variances that I have kept by stopping at m. I also know what is the total variance, because the total of the variance is just a summing up all the way to d. I'll put it differently. So if I want to ask how much variance I have discarded, I can just look at the differences that between all the variances, which is summing up all the eigenvalue from 1 to m, minus the one from summing up from 1 to m. 1 to d and minus 1, like 1 to m. Right. And of course, like this means that in many cases, it's very useful to plot the cumulative of all the eigenvalues as a function of m. Then you can decide where to truncate, because the cumulative of the eigenvalue tell you about at mth, like if you stop at m, how much variance you have captured. So if this seems like a bit like mathematical, like we will go to an example that you should know. It's called MNIST. So MNIST is basically a small sample set with 60,000 examples with handwritten digits. Most of them is just like trying to classify the hands written digits. Each of them is 28 times 28 pixels, so you have a total of 784 pixels, meaning that each observation can be regarded as a 784 pixels. By the way, I want to use MNIST because I want to also like dispel the connection between machine learning and big data. I think like in astronomy, we kind of synonymize that. We say, why do we do machine learning? We say big data. And why do we need like big data machine learning, right? So they are like synonymized, but actually the Venn diagram like between the two is actually not overlapping like a lot. You can do big data without deep learning, which is what we are learning through these courses. You can do like classical data science and statistics and do pretty good job in dealing with big data. You can also do machine learning without big data, right? MNIST itself is still a sample that people use a lot, even in the most cutting edge research. Right? If you want to understand sort of the theoretical understanding of the neural network, people still look at like MNIST. And MNIST is not a big data because it can be attached to your Gmail without like uploading that, right? So you're definitely not doing big data, but you are still doing like machine learning. So there are really like, these two are very different concepts, but somehow we tend to mix them. Anyway, that's just the gripes. As you know, I like to gripes. Okay, so MNIST, right? So if I take the digits of 8, just taking subset of the images of 8, run the PCA, do the diagonalization, and calculate the cumulative sum of the eigenvalues, you will get something like this. So this tells you that, let's say if I want to keep 50 dimension out of the 784, I will capture about, like 70% of the variance. If I keep up to like 100 like vectors, then I will keep about 90% of the variance. So just by plotting the cumulative sums of the eigenvalue, then you get a sense of how many dimensions you need to keep in order to have a fidelity reconstruction of your data, how much you are throwing the information, assuming that the information means the variance. Question? Cool. And this is also one example showing that even simple things as simple as like MNIST, in real life, like scenario is actually much more complex than astronomy because the variance grow pretty slowly. So even out of the 800 dimension, you kind of need to keep up to like 150 to keep most of the variance. So 1/5 of the dimension. Whereas in your quasar case, in your assignment, like 7,000 dimension, you can compress into like 5. You capture all the variance, right? So astronomy is very simple in the lens of the variances. Yeah, so that's basically conclude the overview of PCA, but still there's one trick to be mentioned. So remember, right? So in order to do PCA, you only need to do one thing: calculate the data covariances and do the diagonalization. This matrix is a D by D like matrices, where D is the dimension of the features. As we mentioned, right, D can be very, very large. I can take spectrum, I can have 10 pixel, 10,000 pixel, and to diagonalize a matrices have a complexity of d cube. So if I have a 10,000 pixel, you know, you can sort of like run that and watch a YouTube video, and then you will finish, right? That takes some time. In many cases in classical machine learning, it turns out that it's possible to have n is smaller than d. In modern day deep learning, this never happens because to train a neural network, you need many data. But for classical machine learning, you can deal with the cases where the data is very sparse. So you can actually run a PCA on 5 spectrum, even the spectrum have like 10,000 pixel, right? So it's possible that n is smaller than d. Then in this case, you really do not want to do the diagonalization of the d by d matrices. You want to find a trick. Maybe I can do a diagonalization on the n times n matrices. And turns out that like this is possible. Why? Because let's remember the matrices here is d times n. So the x times x transpose is d by d. The goal here, if n is very small, then you know that these matrices cannot be full rank. In fact, most of the eigenvalue has to be like 0. If you have not learned the linear algebra, it's just saying that if I have like only n data point, like let's say 5 spectrum, at most, I only need to keep 5 vectors, right? I will exhaust all the information if I keep all these like 5 vectors. So the data covariances that despite to be like 10,000 times 10,000, there's no more than 5 vectors that I need to keep, or meaning that all the other direction has to be trivial. So the goal here is like, does there exist a n by n matrices that will give me more or less the same like calculation? But there's one problem here because we already show that we really want to diagonalize the S matrix, which is the d by d matrices, and the eigenvalues of this diagonalization have a physical meaning. So if I want to substitute that with another like matrices, at least one thing that we need to satisfy is they have the same eigenvalue. So I can sort the eigenvalue as I would if I have done the d by d like matrices and use this to make the decision. The other thing that you want to make sure that you can transform it back to the original eigenvector. Let me show. It's clear that for any n by n matrices, your eigenvector will not be the same, because your eigenvector in the n by n matrices will be a n-dimensional vectors, and your eigenvector in the d by d matrices will be a dimensional vectors. So you want to find a way to transform it back while ensuring that diagonalizing these matrices will give you the same eigenvalues. It turns out that like this is possible. So like remember, if Bm is the eigenvector of S, I have this to be true. So now S is just 1 minus n times xx transpose. I can multiply x transpose on both n. Now I redefine this one to be C. Then I get to this same stage, right? So I have 1 over n x transpose x cm equals to lambda m cm, where x transpose x, unlike xx transpose, is an n by n matrices. More importantly, it shares the same eigenvalues. This seems like magic, but actually this is a very common trick that you will see that like again next week when we talk about the Gaussian process. So they're always like a n by d matrices. You can look at the d space, or you can look at the n space. So this is called the kernel trick. But for this now, just saying, we have transformed this into a smaller matrices when n is small, while sharing the same eigenvalues. Right, so I have the same non-zero eigenvalue as the data. So you can rank the component as you would using the eigenvalues. And it can be much more like efficient because now you are diagonalizing a n cube operation instead of a d cube operation. But still, there's one thing to solve, because the diagonalizing X transpose X only gives you the vector Cm, which is a vector in Rn, not even in Rd. So how do I transform it back to the eigenvector that I want to find for the original S? Turn out that, again, you have both sides. You can look at the N space or the D space, right? So we know that this to be true. If I now multiply this X on both the left-hand side, then we get to this one. Then if I redefine this one to be S, then I see this one, right? So meaning that even I get Cm, the corresponding eigenvector in the D space will be just X times Cm. So I solve the computational complexity while being able to sort the eigenvector as I want it to be. So that's a trick. By the way, I mentioned this because this is a good introduction to the kernel's trick to transform D and N dimension, which will come back to the Gaussian process. In practice, this might be good, but as you will see in the tutorial, there is a better way to do the diagonalization. Not better way, a more algorithmic way. So this gives you either N cube or D cube. So you can choose if you want to do a D cube or N cube like operation. More practically, you can use what we call the SVD, as we will see in the tutorial, that will give you a complexity of N squared D, I think, or D squared N. So it's like a good mixture. It's like never N cube or D cube. And in many cases, for a normal N and D, then you do not need to do this transformation. But it's true that in some cases, because you are still like N cube, like N squared D, you might still win by doing N cube instead of N squared D. Therefore, this operation, if you have time to code up a few more lines, it will be more efficient, especially when N is really large or very small, or D is very large or very small. But for most of the practical reason, the one in tutorial give you a mixture of a complexity of N and D seems to be quite good. Okay, so to recap what we have done today, you have a bunch of data point. In order to run PCA, you will shift that to have a mean 0. And then if you have different dimensions, sometimes you need to democratize all the units. This is a choice, depends on how you think about which unit is more important. Is 1 Kelvin more important than 1 gram, or it's 10 Kelvin equals to 1 gram, right? That's your choice. But the easiest way is to just divide that by the standard deviation, and then you calculate the data covariances matrices, do the diagonalization, and then you find the direction, and then you do the projection, and then call it a day. You will also explore that in your assignment tree. So after today, you should have all the material that you need to solve for assignment tree, which due next Wednesday, 11:59 a.m. So not midnight, noontime. Yeah, and also the lecture for next Thursday will be on Wednesday, because I'm going to give a TED talk, so I cannot do on Thursday. So it will be 2 p.m. here on Wednesday. So after you submit your assignment, you can come to listen to the new lecture. If not, I make a poll, I think that's the best time, but I will also record it. So the lecture will be recorded. Yeah. And will be the same lecture hall. So we'll be here 2 p.m. Wednesday. I will send out another email next week. So key step of PCA, right? So first you have some data. You will subtract the mean. You might want to divide that by the standard deviation if you want to democratize all the units. But this might not be need to be done. It depends on what you want to do. After that, you have a bunch of data which allow you to calculate the data covariance matrix. And then you do the dot product of the data covariance matrix, will give you the S. And then you will diagonalize S to find the eigenvalue and the eigenvectors. And then you will sort the eigenvalues. And you will do a cumulative sum of all the eigenvalues, look at the plot, and decide how much of the fractional variance you want to keep. Truncate that at m dimension. And then if in some n is much smaller than d, you can do the x transpose x. In this case, you need to transform the eigenvector back by multiplying by x. And then now you have the direction, a bunch of b, the dot a product of them will give you the new coefficient. So the other b here is just to say the direction, right? So voila. So after that, you have the transform projected manifold. Of course, you are still in this strange unit that you have a transform. You need to pull it back by doing the inverse transform, and then done, right? So that's PCA. So what we have learned today, we talk about another task that we have not touched upon in unsupervised learning is a dimension reduction. PCA is one of the quintessential canonical tool to go to for good reason. You can see that the math are simple, but actually is quite beautiful and is quite elegant. We talk about this is a projection to the manifold, so we learn some projection. We are based on the idea of maximum the variance. Turns out that practically you just need to diagonalize the covariances matrices and find an eigenvalue and eigenvectors, and then you are good. Any question before I go to the tutorial part? No question. I'm going to drink water. Okay, cool. Let's go to the tutorial part, which again, lack of time, totally unprepared for that part. Okay. Let's walk you through a little bit of the tutorial. Oh, hopefully no one say, oh, you forgot to share your screen. last time I need to do that again. Oh, okay. Let me see, tutorial 9A. Oh, and most of the tutorial and lecture is already uploaded, except for next Tuesday one. I think it's on autoencoder and mixed density network. I haven't prepared that. Also the last lecture, which is on the LLMs. Yeah. So but the other lecture and tutorial are mostly uploaded. So let's play with this thing. Let me mess this up. I was hoping to use a more astrophysical example, but turned out that run out of time. So here, using Pokemon, which is better anyway. So I was hoping to use the images of galaxy, which is 1-to-1. You can swap that out. So the most of the thing that we will be doing today, you can also apply that to the morphology of galaxy images. But this time we'll look at Pokemon. That's so cute. Ooh, so cute. All right. So the goal here is to find the eigen Pokemon. So if you collect all the data and you do the diagonalization, you get the eigenvector. By definition, is the eigen Pokemon. What is the eigen Pokemon? It's the direction of the images that will kind of like give you the most structure of the Pokemon, right? So the most direction that you should keep. The eigen Pokemon looks like this. So like most Pokemon looks like, there are some wings, some blah, all Pokemon looks like the same. Interestingly, as you have learned in your assignment 3, if you combine PCA and generative models, you can sample the coefficient from PCA and reconstruct things. So meaning that you can make new Pokemon from the eigen Pokemon, Eigenmon, right? So that's the goal, to get the eigen Pokemon and looking at the inverse and then try to reconstruct. So this is the real one. If you only save like a fraction of dimension, then you can see your Pokemon get more fuzzy, but most of the structure are still there. I can assume you that like galaxy like images is much easier, like especially the elliptical galaxy. It's like only like 3 components can capture most of that. And we know that for a long time because the elliptical like galaxy have what we call the Sersic profile, which is only like 3 parameters. So you expect if I do a PCA, then I should be able to capture the overall structure of what is a galaxy, right? I was hoping to swap this out for galaxy like images, but what is time? So Sorry. Hopefully, like if I have time, I might update this tutorial with include the galaxy like images. But if not, like we will do that for the autoencoder part. Okay, so this is the tutorial. The next step is me having fun with Copilot. That's always the I can walk you through the code. Oh, let me walk you through the theory first, because this is interesting. I remember we talked about the covariances like matrices is just S equals to 1 minus N times XX like transpose. And then we say we can diagonalize S, which is true, then it's done. But that come with the cost of either D cube or N cube. Depends on if you're doing XX transpose or X transpose X. There is a median way to do that. I'm not sure like you have watched A Good Place, which is an amazing like series. There's a good place, there's a bad place, there's a middle place. And the SVD is the middle place, right? So the idea of the SVD is to say, well, I do not need to look at S like itself. For any matrices X, even this is not a square matrix, it's a rectangular like matrix. For any such a matrix, I can decompose that with some what we call the SVD decomposition. So SVD like decomposition is to decompose like any like matrices X into some triangular like matrices U and V, and some diagonal like matrix lambda. And sort of the diagonalization, and you also guarantee that the U and V, the dot product of them is identity. Why this is nice? If you decompose X into U, sigma, and V transpose, then this, when you swap this, then you get like U transpose U, which is the identity. So you're left with just 1 minus N V sigma square and V transpose. So what this means is you have already like diagonalizes S, because this matrix itself is diagonal, and V itself is the eigen vectors. Sorry, I don't think they are triangular. It's just V and U are some matrices that the dot product is identity. So what this means is that without diagonalizing S, but just running SVD on X, you can get the eigenvector and the eigenvalue. And because we are doing an SVD on a X matrix, which is the N by D like matrices, if you do all the complexity, I forgot which way, I think it's N squared D or D squared N, then you're in the middle place. You're never N cube or D cube. You have some mixture of the complexity between N and D, which is in most cases quite reasonable. So that's sort of the what we do here. In like sklearn, they also SVD to PCA. No, I think I write this, but I think the one that is implemented in sklearn is using the SVD decomposition. Or put it differently, in some cases, the one on the sklearn might not be the most optimal, because if you load, like you always have a preference of N and D, you can always like write your code to make sure that it's not so expensive. Okay, so that's the theory. This is the part to make eigen Pokemon. Probably don't want to do the SVD part. I mean, like, I'm very bad with the column versus row matrices. You don't like me? Okay, use lighting. Okay, so this is I believe this is the dimension of the pixel, because this is a 64 times 64 pixel. And I have 179 Pokemon. Plot one Pokemon. Let's see. Oh no, this is 60. This is so dumb. I mean, like, you can take the square root. It's completely dumb. Okay. Ooh, see, cute. Nice. Okay, so first I want to calculate. If I do the SVD, it's fine, but let me do the simpler one. Calculate the data covariances matrices. Oh, I can do the, okay, this is fine. Let me make sure this is the correct dimension. So I should be d by ds, right? So this is 4,000 times 4,000. So meaning that I am using the correct notation, because sometimes you forgot like if you want to transpose or not. Remember, the main thing is the covariances should be d by d, where d here is number of features, which is 4,096. Let's see if it would run the diagonalize. I'm a bit worried that the lean algebra might not do a good job, but let's see. Not sure. We can watch a YouTube. Thinking that if you do like more than 1 minute, then I will do the SVD. So this is the problem, because you have a d cube the operation. You can actually do the other way. We talk about you can do the 1,000 times 1,000. Like if you get too hard, then I would do the other way around, doing x transpose x and diagonalize that. Let's give it 1 minute. Like anyone that want to do some knock jokes? Knock. Where's the Pokemon? Okay. So I get this done. Eigenvalue shape is, yeah. So there are 4,096 pixels. Therefore, there should be that, and then I will sort eigenvalue and eigenvectors. That's correct. So I will sort that. Just rearrange that. Plot the cumulative of eigenvalue. Right. So this is good. Make it more X title, late number of components, cumulative variance, right? So here is plotting that I have, in principle, I can keep all 4,000 dimension, but this is a cumulative the variance. So you actually get a pretty quite quick to like 90%. So let's say I want to keep 90% of the variance. So it probably is like some, yeah. So this is where sum is bigger than 0.9. I think that's correct. I think that will do it. That will just from the 154 components to keep like 90%. So now I will truncate eigenvectors, right? Yeah, so I give that, making sure this is the right dimension. The hard part of PCA is just it's like transpose or not. Yeah, so this is, oh shit. Oh, this is hard because I'm not sure. Yeah, I'm not sure this is a column or row. We will see. Like if the Pokemon looks weird, then you know you are not doing things right, because it's a square matrix. Okay, so reconstruct the image with the truncated eigenvalue. First project the data into the eigenvectors, right? So I need to find the coefficient in the new axis, do the b dot x. Just images time projection. Shape. Oh. No, I shouldn't do the truncated one, because yep, humans still have jobs. Okay. So I will project that for all the components, and then we keep the one that I need to keep, right? So this is only the coefficient. Why is it called like images? This is terrible. Stupid. Coefficient. Yeah, this should be called coefficient. So I'm doing b dot x. If I want to reconstruct the images, I will truncate the coefficient to the n component by keeping. Yeah. So for individual Pokemon, I will keep the 154 like coefficient, and then we will reconstruct Pokemon. Reconstruct images. How does it reconstruct? I will just b transpose x, right? So if I project that into the whole vector, I will get back the images. It's not defined. Why? I haven't run this. Okay, cool. Okay, so now what is the print images reconstruct? Okay, this is very correct. Compare the first Pokemon. Subplot. Image 1, original. Image 2, reconstruct. Complex. Why is it complex? Crazy. Oh, because eigenvector give me complex number? No, cannot. I mean, the eigenvector has to be real. Why? This is very strange. Type. Why is it a complex? Oh, image 3 state complex number. Ooh, no type. I forget all this command. Check type of image. Type. Oh, okay. That's fun. That's correct. Oh, NumPy array. Oh, see, D type. Ooh, is it a complex number? It's very strange because like none of this is really doing any complex operation. It's okay. Let me see if just like something take the real part. It's very strange. Okay, let me see if this looks real. Yeah, it's okay. Looks like a Pokemon. Keep more. I think we can keep. I don't know why it gave like a complex thing. I'm thinking like it's the diagonalization, but it's very strange. Your matrix is real. Your diagonalization should be real. Yeah, I don't know where it goes wrong. That is the very interesting part. Let's say I have 95 thing. More features, less thing. If I keep all of them, then it would be the same, right? So if I do, making sure, yeah, I'm very worried about the weird part. So if I just do the coefficient project and all the whole thing, it will be the real construction, but I'm using the real space. Yeah, it's the same Pokemon. Very strange about the complex part, but I couldn't figure out why. So this is the Pokemon, but you can also do that in SVD. So we have 15 minutes. So let's do that with SVD. So remember here we done like how many seconds? Like 38 seconds. So let's see if it can do this like faster. Redo this images, still the same. Let's try another one. What do we have? It evolved. Another one. Ooh, become stronger. Cool. Let's do the perform SVD. SVD on X, on the images. So, this is the images. Like if you like, this is exactly the calculation that you need, because when you have done that, 3.9 seconds, right? So it's much faster, and the rest you just need to do the eigen value is just S square, I think. Yeah, S square divided by sum of S square. Why do you need to divide? Very strange. But anyway, it's just like a sorting, so it does not matter. I don't think this is correct. I think just S square. You can, but since we are doing the cumulative, that's fine. The cumulative of sum, sum. Yeah, so this means that your sum, you don't need to do the divided by sum. So the same curve. The eigenvector is just V, right? So we talk about once you have done the SVD, it's very handy because you never need to see S like itself. You already have the eigenvectors. So the eigenvector of S, I think it's just V transpose of V. It could be whichever direction. This is also a square matrix, so I'm not sure it's helping. But at least I can check it should be a 4096. Very strange. Because I'm doing SVD, when you have a square matrices, is like do not calculate all the eigenvector. You will calculate up to like 1000 dimension, because you have a D by N matrices, so you cannot calculate all N direction. But in principle, your covariances always like truncate somewhere here. So this is fine. So we can skip this. We call this eigenvec. So let's call that eigenvec. Do the same thing. And then I will truncate eigen. Did we call that eigenvals? Eigenvals. Wow. right? So this is eigenvals that will choose the component, same number of component. That's encouraging. And then I do the truncation, and then I do the projection, and then I do the truncation of the coefficient, and then I do the same thing. I think that is called trunk images. Hopefully this is real. Still complex. I don't understand where you give me the complex thing. A Pokemon. Choose another one. 4. Ooh, nice. Okay, so you can do the galaxy images, but important things here is, in many cases, we don't care about the reconstruction, but we want to have the representation of the images. So your projection, like coefficient, is a representation of your data. It's a low dimensional representation, and then you can do things on that, right? So if you do a logistic regression on this, it will be like really hard in all pixel. But if you have compressed it down to the coefficient like 100 dimension, then you can run a logistic regression to separate out the evolved Pokemon and not the evolved Pokemon, or like elliptical galaxy or spiral galaxy. Actually, I will try to include the galaxy like images to do the classes separation. Oh, you see, we have like 10 minutes left, but any question? If not, we can end earlier today. Yep. Right. Right. Yeah. Yeah, I think that's sort of the one thing that is, in principle, you can absorb that in the covariance matrix to do is X transpose X. What is typically done, like especially what I have done for the PCA, like paper for the chemical space, is you expect some of this the variance is due to noise, right? Some of the variance is just so what you can do is you can run some simulation and see how your noise translate into the variances in this space, and that will give you a cutoff. So PCA is also like somewhat a denoising process. If you know your noise is orthogonal to everything, so keeping that will help you to denoise the data. Yeah. Yeah.
Will that ever increase the accuracy with the model? For example, MNIST.
Right.
Do PCA and do the same model, you get a higher accuracy.
Like classification? No. I mean, like, yes and no. I mean, like if you reduce the dimension, then it will give you more powerful way to deal with some classical tool, where you might overfit or underfit quite easily in the raw space, but in the compressed space you can do like better. But in the modern day deep learning, when you compress the information, you are losing some information. So this is why, for most of the cases in the light of deep learning, all these methods just make things more interpretable, because you have a eigen Pokemon. If you do a classification and see that some of the component is more important, then you can say, why this is an evolved like Pokemon? You might say, well, you know, it has wings, right? So the wings might be a very important like component that decide if something is. So it will help you to give you some interpretability compared to like deep learning. But of course, you are compressing the information. So if you want to do a very good job at like doing like inferences, you try not to compress the information. Yeah. Hmm? Oh yeah, you can do that all day. Yeah, you don't have the notebook. It's all on generate new Pokemon. We can do that. So you can run GMM on the coefficient. So first you need a generative models on the coefficient space. Yeah, now I'll use the sklearn. That's fine. So create a sklearn three component. Sure. Fit the GMM. I will fit all the coefficient. I think coefficient. Let's do a 200 dimension. Let's truncate that more. Let's truncate that to, I don't know, keeping 80%, right? 80%. They just give me like 68 component, which is doable. So I need to make sure that I truncate my coefficient. Where do I do that? Okay, so now I have 68 dimension with 180 objects. So of course I can fit a GMM. Let's see, is that run? Watch YouTube. Not sure. 1000 object for 68 dimension. It shouldn't be too bad. I mean, it might be under constraint because too many dimension. I will probably make a assumption on the covariances matrix. Remember when we do GMM, you can do a full covariances, which has a D times D like complexity, or if you do a diagonal. Yeah, if I do one component, you would so one component GMM is PCA, right? So you are feeding one blob. Why is it not liking it? Oh, did I do something wrong? Did I? Print coefficient. It's very strange. Okay. There are many strange things happen today. That's not very usual. I wonder if when we run GMM, it transmute the array. Oh, it frozen and then it kill everything. It's also possible. Complex data is not supported. Okay. But not completely missed. This is there, right? Okay. So, yeah, I think they're real. Yeah, I think it has to be 0. It's a symmetric matrices. Just not sure why it give me complex eigenvector. Take the real one. Yeah, getting more dumb and dumb. I do not know how to code now. Okay, so I have this component which do that. Ooh, complex data is not supported. Why? Wait, are you crazy? Okay, new sample from the GMM. So I make a models. I'm basically like giving out the solution for assignment 3. All right, so I make some new sample. So this is okay, and then make new Pokemon. So now I have a new set of a coefficient that's drawn from the same distribution, estimated by GMM. Make new Pokemon. You might need to have a complex value. Yep. Make this complex array with 0 imaginary part. So it works. New Pokemon. Oh, because I haven't truncate my eigenvector. That's fine. Eigenvec. Okay. This should do dot the product. Okay. Plot new Pokemon. Plot 10 new Pokemon. It's probably pretty fuzzy. It's like 68 like percentile. Oh, what is that? Okay. All this is complex thing. np.real. New Pokemon. Yay. They look somewhat like Pokemon. They are fuzzy blob of wingy object. Yeah, so this is also like how you can make like new quasar spectrum. Actually it's like real research. People do exactly what I do, like PCA, the continuum, do GMM, sample from that, make new quasar, populate that in your simulation. That can be easily a lot. People do realize that like a lot of paper you can write, right? A lot of people, there are lots of things that are very straightforward and is to demystify a lot of like research. When you learn this like systematically, there are lots of things that become quite useful in research. Okay. Anyway, we have 2 more minutes besides making new Pokemon. People are happy? Okay, we can finish early. Thank you. See you next Tuesday.